My name is Tim, this is Seán, and we are here to talk about our experience at Demonware deploying Cassandra for Call of Duty. Tim Czerniak, that's me. I'm a software engineer. This is Seán Sullivan, he's an operations engineer, and we both work at Demonware. Demon who? Demonware is a subsidiary of Activision Blizzard. Activision Blizzard is the umbrella evil corporation, and we're owned by them. And generally speaking, their model is that they kind of own a bunch of studios and smaller companies who all work together, and they kind of leave them be for the most part. So we're one of those entities. And what we do is we write and deploy and maintain client-server applications for Activision and Blizzard games. So what we've been working on this year, we did a bunch of stuff for Call of Duty Advanced Warfare, which released not very long ago. It's doing pretty well. Diablo Reaper of Souls on the console. We didn't work on the PC version, but on the console versions we did a lot of stuff, which is earlier this year. You've got Skylanders there. Trap Team came out not too long ago. We do a lot of stuff for the little figures that go on the podiums and appear in game, and all the kids love it. And then there's also a title in China based on Call of Duty, which is releasing just for the Chinese market early next year, that we've been working on as well. And there's also Destiny, which isn't there, but Activision works with Bungie, who originally did Halo, and they're working on Destiny, which is like a big MMO. We also helped out with that. So some of the stuff we've done in the past, every single Call of Duty since Call of Duty 3. There's one every year, and we've had a big hand in all of them. A bunch of Guitar Hero games in the past, DJ Hero, Band Hero, all the heroes, GoldenEye, all the 007 games, and Skylanders, and a bunch of other stuff. I think we have we're on the 102nd title or something that we've been involved with at this point. Lots of stuff, and so we provide services. So things like matchmaking. So you want to play a game, you want to shoot someone in the face online. You say, I want to shoot someone in the face, and someone else goes, hey, I want to shoot someone in the face, and they both talk to the matchmaking service, and then we match them up, and they go and shoot each other in the face. So we do things like leaderboards, chat, file storage, progress storage, which you'll hear about in a little bit, leagues, social network integration, et cetera, et cetera. We have about 100 services or more. I can't even remember at this stage. And yeah, lots of stuff. So some of the technologies we use C++ for the client, because of course games are all written in C++. So we give the studio that's making the game a library written in C++, and they integrate it into their game, and hey presto. We also use a lot of HTTP-based stuff, like we integrate with websites, and we have lots of RESTful web services internally and all that kind of stuff. And on the server side, we use a lot of Python, mostly Python. Erlang as well, MySQL mostly for databases, and we run everything on CentOS, and we use Puppet for automation. They're the kind of main things. We have a lot of technologies in our stack, but they're the kind of big players. So we have a slightly unusual use case. Most services, you start a company, you start small, you get a few users, you might gain a bit of popularity, you'll gradually grow in popularity, and gradually get more and more users, more and more people online. You might get a couple of spikes if someone writes about you in some famous website or something, but generally speaking, it's like a slow and long uphill scaling up. For us, we get the exact opposite. So on day one, a game launches, everybody goes online. And then gradually, over a long period of time, maybe a few years, it'll tail off. So you can see here, this is an online users graph for one of the Call of Duty games. There's the release date, you can see. That's the first weekend. That is the peak number of online users for the game ever. And that's Christmas. So you can actually see the weekends there as well. So you can see that's the run up to Christmas. So in the words of Benjamin Franklin, by failing to prepare, you are preparing to fail. We need to be pretty certain that our services are going to work on day one, because if they don't, you're going to have a lot of angry gamers at your doorstep. And so we need to be very, very prepared. So I'm going to pass on to Seán. He's going to talk about a predicament.
So our predicament is typically we have one title per DC, or we isolate titles per DC into single clusters. So we don't generally share data between titles. That changed for Ghosts, where you had new platforms, you had PS3 and PS4, and Xbox 360 and Xbox One, and people would often want to play in 360 and then buy the new copy on Xbox One and migrate and keep on playing from where they left off. So we need to share data across DC. MySQL is not great at doing that. It would mean because you can go from PS3 to PS4 and then continue playing PS4, and if you have friends on PS3, hop back on PS3. So we need to be able to write to both and read to both. And we weren't prepared to have MySQL because we also have a sharded infrastructure as well. So we looked at using Cassandra, looked at using a non-relational database for some of our services. So we brought it down to about 4 services, which were mostly non-relational key value type services. The first service was the progress store. This is kind of a blob of data. We don't really know what's in it, but it's typically used for what level you are, some of your stats, your loadouts, so what guns you've equipped, that kind of stuff. It's the read-write ratio for that is 1 to 4. Your file size is pretty small, it's before 4 kilobytes, and it's persistent data. So it never goes away. You always want the loadout to be there, you want the level to be there, all the information about the player to be there. The next one is presence. So the presence service is when you go online, you typically say, hey, I'm online, and you write to the service. And you'll write to the service a few times a minute. When people check what friends of mine are online, you'll check the presence, your internal presence, say, is this guy online, which of my friends are online? So again, the read-write ratio for that is 1 to 10, where you're reading quite infrequently, but you're writing all the time to make sure that the information is correct. The data size is minimal. It's pretty much just a case of users online and some very small metadata. It's transient data as well, of course. The messaging service is quite generic. It can be used for messaging, it can be used for game invites, it can be used for mails, it can be used for any kind of that kind of messaging type stuff. Again, read-write ratio is 50 to 1. So you're constantly checking, do I have emails, do I have invites, has something changed, has someone sent me a message, but the actual people sending messages will be quite low. And again, transient data, because once you read it, it's deleted automatically for you. So our requirements, as I mentioned earlier, first requirement is cross DC. As I said, we sell it by title, so we typically have 1 cluster per title, or a group of titles. So it could be a title like PS3 and Xbox One, or that kind of title. That might be 1 cluster, and then another cluster might be PS4 and Xbox 360. The next part is consolidation and expansion. So as Tim mentioned, we typically have our biggest growth on the first few weeks, and then it kind of slowly eases off. That means we spend a large portion of our time consolidating hardware, making clusters smaller, because again, once Christmas is gone for certain titles, that's kind of the biggest boom. So we need to reclaim back hardware from that. And expanding again, sometimes we'll add titles to current clusters, so we need to make the cluster larger. So we need to make sure whatever we looked at, we could easily consolidate and expand the clusters without much effort. We've been using MySQL for approximately 10, 11 years at this stage. So we're pretty confident in it. We can do it well. We've got a lot of tooling around it. We've got a sharded setup, which means we can just keep on adding write throughput to MySQL without issue. So we need to make sure whatever system we chose, we could manage just as easily. We need to be able to automate it to the point where you can have it 1 tick, click of a button, and it'll deploy a new server. It'll add it to the group of the cluster, and the cluster will expand. That's where you need to be at. And also, for the operations teams, we need the case where if a server died, they could easily replace it without much effort. So then, of course, the last requirement was throughput. So we looked at the previous titles we had, and we estimated what the new one would be and require. So the requirements were, for the progress store, 1.5 million requests a minute. For the presence, 250,000 requests a minute. And for messaging, 850,000 a minute. Now again, that's requests from the application layer, so that could actually turn into 2, 3, 4 or more requests at the Cassandra level or database level. So during our Cassandra evaluation, one of the operations engineers came to the office with mismatching footwear. So the joke went around that he was highly available but not consistent. We did require a shift in thinking, going from a relation database to going to non-relational and the whole CAP theorem. We're used to MySQL, we're used to using large, heavy, beefy boxes, and we know how to configure them, we know how to do MySQL well. When you start doing SQL, stuff like Cassandra, stuff like React or Cassandra, using DynamoDB type stuff, you have to really think differently and realize this isn't just MySQL, it's not just on the database, you have to understand the architecture and how it actually works. So we shortlisted 2 available options, React and Cassandra. And the main reason we shortlisted those were they're both DynamoDB, they're both level DB, they both supported vnodes, and it was easy for consolidation, expansion, the tooling was pretty good. We rewrote our application backend twice. So our application backend currently supported MySQL, so we added React and Cassandra support. This meant for load test it was a lot easier. For load testing, we built out 2 clusters. Pretty production-like cluster, but production-like hardware. So the first cluster was single CPU, SSDs, so fast disks, and average memory being about, I think it was 32 gigs. The second cluster, which is different DC, was dual CPUs, spindles, so larger but slower disks, and high memory, so about 96 gigs of RAM, I think it was. So this was a deliberate decision we took because we wanted to see where the bottlenecks were. If we just had one cluster and we did a tweak or did a change, we wouldn't if it fixed one bottleneck, we wouldn't know what the next bottleneck is. Would it be I/O? Would it be CPU? So by having 2 clusters, it meant that we could actually see where certain bottlenecks were and make configuration changes and see how that affected both types of hardware. It also meant, since we hadn't bought the hardware yet for this project, that we could see better what type of hardware we needed and comparing the 2. So we used our own software stack to load test. We didn't have a special test software, kind of software we wrote just to load test. We had our own, the normal software we were using production. We haven't used production. We modified that to use Cassandra and use React. So our load test would be accurate. I think the most important thing we learned from load testing is you have to use realistic data and realistic user profiles. So we can check our development environment, see what calls are being made. We can check our previous production environments to get a rough idea of the quantity of calls, and then we can actually emulate that. And we have our own load test clients which act as users and do the whole login, log out, that whole process. Initially, we didn't include peaks and troughs, so users logging in, users logging off, and that bit us pretty hard, as Tim will go into later. One important thing which I think is needed to do for this kind of test is soak testing, where you run a test for ideally 1 to 4 weeks. Cassandra can change over time, you have more data in it, caches change, that kind of thing. So we only actually managed to get about a 4-day soak test, I think, because time constraints, but we were aiming for 1 to 2 weeks. Some interesting stats of what we actually load tested to. So we load tested our cluster to 5 million users. At the 5 million user rate, we had 6,000 reads a second, 15,000 writes a second, and at that peak, we had 2.5 milliseconds latency at the 98th percentile.
So we load tested React and Cassandra, as Seán said. So who was the winner? It was React. No, it wasn't React. So we thought that React would be a slam dunk because, well, it's Erlang based, and we know Erlang. We use it for some of our stuff. The tooling for React is actually excellent, and at the time it was the first one we did the load tests on. So we thought, okay, this is looking pretty good. Everything is performing well, and we had actually also previously evaluated it for something else. And so we thought, okay, this will be good, this looks pretty decent. But then we did Cassandra, and it was way better. So it won in the end. The write performance was about 4 times better than React, for our particular use case, that is. It had more features. It had compound primary keys. It had partition and clustering keys, and that kind of added to the available query set that you could use. It had SQL, which was a bit more friendly. It was better for our developers. It was a bit more mature. So React was fairly, at the time, this is maybe a year and a half ago. React was a bit. It was kind of a bit early in the cycle of that particular product. So, we were a little bit happier with Cassandra being a bit more mature. The only thing is, I guess, we thought with Cassandra, we were like, oh, Java. A lot of our developers or engineers in general will run a mile if you mention Java. But the nice thing about Cassandra is it really does not, it doesn't reveal its innards at all, really. And so you don't really have to deal with Java. You don't need to know that it's Java, which is great. And it's the way it should be. So that was good. So that was it. Then we just continued testing on Cassandra cluster for 24/7. We have 3 offices, so we have one in Dublin, one in Vancouver, and one in Shanghai. And so we were able to take advantage of that round-the-clock coverage to just monitor the thing and do loads of soak testing, loads of load testing, tweaking, etc. So we had also planned a hybrid solution because we were a little bit paranoid. New technologies make you a little bit paranoid. So we had planned, okay, we'll have a MySQL cluster, we'll also have a Cassandra cluster, we'll write to both, and then we'll read from MySQL, and then maybe we'll dial up the Cassandra reads, and then we have this fancy thing where if something terrible happens to Cassandra cluster, we have a disaster recovery plan where we can migrate MySQL data over into Cassandra eventually, and it ended up being way too much overhead. It was overly complex, too much overhead for our development and ops teams, and we just, at the end, we had load tested so well, we trusted Cassandra, and we dropped that idea. So we just went straight to Cassandra. So the schema. So for the progress store, it was pretty easy. It's a perfect fit. It was, key value. You always know the key. It's mostly writes. Cassandra loves that. The presence was a bit more relational. We had 2 tables, and we had an issue with TTL. So it's pretty high throughput. So you get a lot of tombstones, a lot of I'm online, okay, now I'm offline, and you delete a row. And so you get a lot of tombstones. We had TTLs for like failure cases, and making sure that things were cleaned up after a while. And we had an issue where until, as Seán said, the peaks and troughs actually showed us an issue with the schema, in that, or with the TTLs actually, in that we had 2 tables, and one of them was timing out earlier than another. So when people were logging off, you had this thing where after a little while, all of a sudden you get like tons and tons of errors saying row does not exist. And so we were, and we didn't see that until we did a full-scale load test with peaks and troughs. So that was interesting. And then for the messaging service, it's time series data. It's pretty well suited. Cassandra does that well. But we did have an issue with tombstones again. And again, until we had production clusters, we didn't notice it. The Nagios check we had was writing some data for one user, and then reading the messages, and then deleting that data again a minute later, doing the exact same thing over and over and over again. Keep writing, deleting, and so it was building up a load of tombstones in one of the partitions. And so we hit a Cassandra bug, actually, which bit us pretty hard, but it turned out it had already actually been fixed. We just hadn't got it on our cluster, so we duly updated our cluster. But yeah, that was another interesting thing we came across. So the lessons we learned from the schema: keep it simple. It's not relational. You need to relearn things a little bit. Get your partition keys and your clustering keys right, because Cassandra will work very, very well if you do, and you won't have to worry about it. You need to learn how the data will be stored, how it will be accessed before you design your schema. Listen to Patrick McFadden. If anybody went to the training yesterday, that man knows how to do data modeling in Cassandra, so listen to his advice, and you should be fine. Do not ignore the cap theorem. Cassandra's pretty cool because you can tune the consistency. You can say, oh, okay, for this particular query, I think I want a bit more consistency. I want to make sure that that data is right. But you will sacrifice your latency for it. So you need to, what's nice about Cassandra is you can tune that. But you just need to be very aware that when you do, you're going to sacrifice one thing for another. And load test with real numbers, because some schema issues are not evident until you get everybody online at once over a long period of time. So I'm going to hand back to Seán to talk about config.
So again, we started on 1.2 or DSE 3.04, I think it was. At that stage, at least, a lot of the settings that were there by default aren't really right for anyone. We were using real hardware, relatively high spec. The setting was completely wrong for that. Again, looking at it from the VM point of view, we also did a dev environment for VMs for a while. The settings were also wrong for that. So you don't just trust defaults, definitely go in and take a look at the settings. So we kind of took one pass through the config, read it, changed a ton of settings, see this, what seemed reasonable to us to change. One example being multi-threaded versus single-threaded compaction. Changed all the settings and it seemed to be mostly fine, except there was a fair few, well, there was a few we changed at least which didn't go so well, as in that compaction setting, where the multi-threaded compaction was actually slower than single-threaded. During actual testing, it's a case of making one change at a time, doing a full load test, and then seeing the results, comparing the results and graphs to you doing an next load test and making one change at a time each time. If you make too many changes at once, or even more than one change at once, you're not going to see which change actually affected what. We'd have liked to have changed the heap settings, but we ran out of time with load testing. One other example, one of the early changes was the SS table size, where I think the default was 12 megs or something. So we load tested with everything from 12 megs up to 512 megs, and we stuck with 192 megs was the best for us. I think the Cassandra guys now have changed their default to 160, so it's nice to see we're close anyway. So the actual hardware we chose. We ended up going for a kind of a mixture of the two styles of hardware. We went for 2 CPUs, 2 SSD in RAID 1, 32 gigs of RAM, and 1 gig non-dedicated network. That's mostly due to the infrastructure we had in the data center. We typically have an app spec and DB spec host each year. So app spec is typically high CPU, high memory, and low disk. So let's say spindles or smaller disk. Where DB spec will be large disk, lower memory, oddly, and also lower CPU. So we can merge those two specs to create the Cassandra spec. For this spec, for us, the disk capacity is the kind of the factor we have to kind of scale by. So we're really scaling by disk capacity. That's about it. It does mean that in the future we can easily pop the disks out, add in larger disks, and then it'll increase the capacity of the cluster. There was a fair bit of discussion about RAID 1. The Cassandra guys, the DataStax guys, and many people would advise for RAID 0, or forget your node. Your nodes are expendable. Your nodes don't trust them. They're not reliable. Our hardware is actually pretty reliable, so we decided that we don't lose hardware that often. We do lose disks, probably is the most frequent thing that'll actually fail. So we decided to go RAID 1, so at least if a node does go down or we lose performance in one node for a while, we can see it, but we can replace the disk pretty quick, within an hour or two. So we went for RAID 1 because of that. Monitoring. So monitoring is probably one of the most important things you can do in your cluster, if not the most important thing, because if you're not monitoring it, you don't know where the problems are. So the metrics and graphing solution we use is Graphite. During our load testing, we actually help load test Graphite too, because the default metrics reporter, we typically send metrics once a minute. The default metrics reporter sends it once a second or once every 10 seconds. So we have 150 metrics per node, and we kind of hammer Graphite pretty hard with that. The Graphite guy wasn't too impressed. The Nagios check we used initially was one written by Causes. It's on GitHub. I think it's a Perl-based check, which uses Jalokia. So we used that initially, it was okay, but by deploying Jalokia, which exposes JMX metrics over HTTP, it meant we could easily write our own checks, Nagios checks, using Python, and then quite easily have stuff like long-term and short-term checks. We actually look at Graphite data for short-term and long-term usage, average out over the day, and then keep an eye and actually do Nagios checks on if our read latency is increasing or decreasing, that kind of thing. Jalokia is a fantastic way to actually, for non-Java house places, Jalokia is a really great way to actually look at metrics and monitoring for Cassandra, because you can get everything over HTTP. You can also make changes. You can also do your JMX write and kind of config changes or setting changes where you can tell it to flush something over the Jalokia thing too. One of the interesting graphs we hit, which we found pretty weird, was the key cache hit rate. We monitored this for a fair while, and we noticed we're around the 90+%. We're very happy with that, and we kind of put in monitoring checks for if under 90 alert. It wasn't until a few months after we launched we noticed that this metric is actually wrong, or it doesn't actually show you the data you think it's showing. When you're doing compaction, every single read hits the cache. So for periods of time when you're doing compaction, you got 100% key cache hit, which then screws off your actual percentage, which is actually around 70% for us. So the only way to actually get it is by looking at two metrics, by looking at your reads per key space and then looking at your cache hit per key space. You can't actually, one metric for the key cache hit rate doesn't actually work much or work well. Some of the gotchas we ran into. The first one was vNodes and rack awareness. I don't know if this is still the case now. We're still on 306, I think, at the moment. But vNodes and rack awareness don't, as far as I know, work very well together. we saw a 30% difference in data distribution when we had the two enabled. So again, as I mentioned, disk capacity was our main scaling factor, the main kind of limiting factor. So when we start seeing 30% disk usage difference across nodes, that was no for us. So we were using blades. So because of that, we hoped to turn the chassis into kind of a rack and get data moved around that way carefully. We ended up having to ignore that and just go vNodes without rack awareness in the end. Load balancers, so we don't use the new Python driver yet. We're currently using the old Python driver in GitHub. Because of that, we have a load balancer for the Cassandra, and all reads and writes go through the load balancer. Because of that, we need to make sure we'd have a client, each client would disconnect after approximately 10 minutes and then reconnect. Because otherwise, if we expanded our cluster, if we start seeing problems with the number of nodes we had, if we didn't have the client reconnecting, the client would just keep the connection open, it would never actually use the new nodes. And of course, which I'm sure a lot of people hate, dev differs from production. So our development environment was VMs, our production environment was real machines, because cost of hardware. So it was close to launch when we were pretty busy with things that all of a sudden we started running problems in the development environment, where it was crashing, a few nodes were crashing, and it ended up being that we used the same settings in dev and prod. So we needed to modify the settings pretty heavily in dev, like reduce memory, put in compaction thresholds, because we had no thresholds in the compaction. So we had to make a fair few changes there. Eventually, we moved our development environment to production machines, so at least it would more closely match the production environment. We had a new data center as well, so we didn't get a chance to load test new data center because it was being built at the time. So we ran into a few issues there where our Linux builds were running CPU speed by default, so we're wondering why one was slower than the other. The newer, faster machines were actually slower than the older machines because they were actually, the CPUs reduced to 1 gigahertz as opposed to 2. Between data centers, we're using a GRE tunnel. Instead, we use GRE tunnel instead of IPsec, because when we're running IPsec, we saw a lot of network issues around there. And network outages and hinted handoff. So hinted handoff, when we see network outages, and any prolonged network outage we had, hints started building up in nodes. So we had to keep a very close eye on hinted handoff and do NIGAT alerts around that to make sure that if we had downtime for a considerable amount of time, we'd actually just turn the hints off, turn hinted handoff off completely, and then do repairs to actually repair data. Because if hints start building up for long periods of time, again, disk space are a primary concern there. So launch. Launch was boring, thankfully. The week of launch, when the development manager came over and requested we simulate node failure, he was a bit concerned. You know, we'd test some of this in load testing, but we never actually used it in our production systems. So I was quite pleased to be able to tell him the first week of launch we had a node failure, and the user didn't notice, there was no impact. It was nice. 2 nodes again died over Christmas. This did impact us a little more than we expected. The nodes themselves dying didn't cause any problem or impact. The problem and impact came from the repairs. We started up repairs in the Cassandra cluster. Again, we have 2 clusters, 30 nodes in each DC for a larger cluster, and the smaller cluster is 16 nodes in each DC. So when 2 nodes failed out of the 30 nodes, we had to run repairs on both sides of the data center, and repairs started hanging, which is quite common in the 1.2 branch. So we started seeing latency increase by a factor of about 4. Now for us that was fine because we're still, our latency, our application then can handle that. But it caused alarm bells for a while, and it meant that during Christmas, instead of saying a node's failure we can deal with after Christmas, we had to actually kind of go in there and fix it and keep a very close eye on it. Also expanding to other titles. So this was built for Cassandra for Call of Duty Ghosts. We expanded it then last year to use Diablo 3 Reaper Souls, also uses it now, and Call of Duty Advanced Warfare uses it too. And we're planning to expand more titles onto the same clusters. So any new title we're building, we'll start pushing more and more to Cassandra, because from manageability and operations point of view, it's a lot nicer and easier to use, and you don't have to worry about sharding, expanding, consolidating the cluster, it just becomes easy. Questions? And I've thrown some of our config changes made into an appendix at the end. So,
Hi, I have a question about the repairs. You said you are running them.
Yep.
Which is very good because they are really, really useful. But I would like to ask about how you actually do this code. Can you hear me? Is it on? Yes.
Perfect. So the repairs, how do you go about running them?
We don't, so we kind of break the kind of Cassandra advice where they say run a repair once a week, or run a repair once a week, or run a repair less than GC gray seconds. We don't do that. Our nodes don't change that often. So we typically run repairs if there's any change in topology or we change any node, we'll then run repairs. We don't run repairs frequently. When we do, we've scripted it ourselves. So we have a script that we run from one node. It creates a lock file. It has to be run on the screen, creates a lock file, gets a node list, hops onto every node, does a repair there. If that finishes successfully, goes to the next node. So I think the Ops Center has a repair service, which is kind of designed to run all the time. We don't really want that because that impacts latency pretty heavily. So instead, we just have the script thing that we run when needed.
Okay, thank you.
Cool. So the talks have been delayed by half an hour. This started late, and the rest will start late too until lunchtime. I think lunchtime is being halved to half an hour. So the rest of the day after lunchtime will proceed as normal.
Just also, I'll do our recruiting pitch as well. We are also hiring, so if anybody is interested in dev or ops, come talk to us. So, thank you.
Thank you.